Okay, so we are on lucky number 2, chapter 2 here. So we started talking about chapter 2 last time, and we talked about really, I think, sort of the structure of the atom. We also talked about some important sort of experiments that led us to the understanding of the structure of the atom. And then we sort of finished up, I think, talking about a couple of things like atomic number. And remember, the atomic number is the number of protons that there are within an atom. And the atomic number can be found up there on the periodic table. So up on the periodic table, you can find the atomic number, which would be 6. So for example, carbon there is number 6. That tells you in a neutral carbon, as we talked about, that it has 6 protons. Also, if it happens to be neutral, remember that the atomic number will also give you the number of electrons, which are obviously the negatively charged particles in there. In this case of carbon, it would also be 6 for the electrons. And but remember, as we talked about, that it is only the protons, which is technically the definition of atomic number. The mass number was the other guy that we looked at, and the mass number was the number of protons plus the number of neutrons. That number is not on the periodic table, and that is not the number that is on the bottom. We're going to actually talk about what that number is on the bottom here in just a second. But all of those things that you calculate, like we talked about last time, the number of protons, number of electrons, and neutrons, plus the atomic number and the mass number, they all should be whole numbers. And that's a good way to remember it. We look on the periodic table, which the atomic mass is actually the number on the bottom there, not the mass number. All those numbers are pretty much, most of them, decimal type numbers and stuff like that. So that's a good way to remember not to write that number. So again, only the atomic number up there on the periodic table. We also talked about, I think at the very, very end, the idea of things that have charges, and those are things that are known as ions. And those are guys that basically carry charges. There's really 2 types of ions that we talked about, which were cations, which are positively charged, and there's anions, which are negatively charged. And sort of the result or the impact on protons, electrons, and neutrons when something does gain a charge is, as we talked about, it is just the electrons that change. And the reason for that, as we talked about the other day, the number of protons or the atomic number is specific for each element. So we can't change the protons, because if we do, we're obviously changing the element. So the only thing that changes when somebody gets a charge is basically they either gain electrons or lose electrons. Things that become positively charged or cations will lose electrons. And that's why they really become positively charged, because they now have more protons, which are positive, than electrons that are negative. So they end up with a net positive charge. And anions, on the other hand, are the guys that will gain electrons for pretty much a similar reason. Because they gained electrons, they now possess more negatively charged electrons than positively charged protons, giving them a net negative charge overall. The effect of that is when you're doing something like an isotope, like say nitrogen, I think we looked at this guy. We would, again, by the way, top left is the mass number, right? Bottom left is the atomic number. So in a situation like this, we would know that this nitrogen has 7 protons because of the atomic number. When we look at a negative charge, the negative tells us it has gained, and the 3 tells us it's basically gained 3 electrons. So we know that the neutral guy should also have 7 electrons plus it gained 3, which means we should end up with 10 electrons in this case. That 7 positives and 10 negatives does give us a net of -3 left over, which again is essentially where the charge comes from in this case. Obviously similar with our positive guys. Any questions on any of that stuff there that we talked about last time? Okay, so continuing on here, we're going to get into chemical composition, and actually the other number that we see on the bottom of the periodic table. The other number that we see on the bottom of the periodic table, again, is the atomic mass. So when we look at something like hydrogen, it says 1.008. That again is not the mass number, but is the atomic mass. It is a fundamental property basically of an atom is mass, but atoms, as we talked about, are extremely small. which means you can't really pick one up and kind of put it on a scale or a balance or anything like that and weigh it. So typically speaking, in chemistry and a lot of sciences, when we can't necessarily kind of directly measure something, oftentimes what they will do is pick something to use as sort of a standard to compare everybody else to. And for atomic masses, they basically used an isotope of carbon. They used the carbon-12 isotope as the standard to compare everybody else to help determine the atomic mass. Something like carbon-12 has a mass of exactly what is known as 12 AMU, which is 12 atomic mass units, which technically is one of the ways that we take the number off the periodic table and use them as units. The unit associated with it is atomic mass units, and that is per atom that you take off of the periodic table. We don't usually use that unit all that much later on. We use it as grams per mole, which is a similar type of unit. But one way you could represent those numbers on the bottom is as how many AMU there is. So what they did with the atomic mass is they basically did experiments, and they showed that something like hydrogen, for example, is only about 8.4% as big as the carbon-12 isotope, which is what they were using for the standard. So they did like a very kind of simple math here. This is 8.4% converted into a decimal. Move the decimal place 2 places to the left, or divide by 100 to do that. Times it by 12, which is the atomic mass of carbon-12. And they get about this number here, which is the number that we do see on the periodic table, 1.008. Again, depending on your periodic table, there will be maybe a lot more numbers. For example, up there it's like 1.007 and a whole bunch of numbers after it. In general, when we do take that number off the periodic table, be it the atomic mass, be it later the molar mass, typically speaking, you usually want to go to about 4 significant figures when you pull that number off. So depending on your periodic table, if you are going to take that number from the underneath the symbol, you'll find again a lot more numbers probably than 4. You typically do round to 4. That's just sort of common practice in terms of how many digits you should use off of the periodic table. Similar calculations were done obviously for everybody else that's up there. Like oxygen is 16 AMU and 55 AMU, and this is really per atom. You know, it's basically 1.008 AMU equals basically 1 atom of it. Now, if we do look up on the periodic table underneath carbon, what we will actually see is what I wrote earlier. I think I might have 12.01. And you may say to yourself, but if they use basically an isotope of carbon as the standard, and that isotope had a mass of 12, why, when we look up there, do we actually see 12.01? And the answer is what we actually see on the periodic table are what are referred to really as average atomic masses, although most people don't call them average atomic masses. And what are they average of? They are the average atomic masses of all the naturally occurring isotopes for that particular element. So if you remember, isotopes are really the same element. The difference is that they have different masses because they have different numbers of neutrons. So there are certain elements, or a lot of the elements will have more than one isotope that sort of occurs naturally in nature. For example, carbon has carbon-12 and carbon-13 isotope that naturally occurs. One occurs about 99% of the time, one occurs about 1% of the time. And they do a little math calculation to calculate the actual atomic mass. And that calculation is we take if we want to calculate the atomic mass like what we see on the periodic table, we basically take the percentage of the first isotope. And the percentage is sometimes referred to as the percent abundance or relative abundance. Is basically the percentage at which that isotope occurs naturally in nature. We times it by the atomic mass of the first isotope. And then the next thing we do is actually add it. And we do a similar pattern. We take the percentage of the second isotope times the atomic mass of the second isotope. And then, if we have 3 isotopes, we just kind of continue that pattern. We take the percentage at which that isotope naturally occurs, convert it into a decimal times the atomic mass of that isotope. If we were to make sure we got all of the naturally occurring isotopes, our percentage should add up to 100%, right? That's when you got everything pretty much. So there could be problems where maybe you're not given a percentage, but you could easily figure it out because maybe you're given a percentage of one isotope and not the other. And if you assume that those are the only two that naturally occur, you can take 100 minus the other percentage, right? And that will give you the percentage of sort of the missing isotope, if you will. So we do this sort of pattern. And again, it's important to remember this is actually a plus. Very common. People always want to multiply those guys. So you're just kind of doing those things and adding it. You obviously could convert the percentage into a decimal by, again, one of two ways. You can move the decimal point 2 places to the left, or again, you can divide it by 100. We'll move it for you if you want to do that. So let's take a look at really carbon here. So these are the two sort of naturally occurring isotopes for carbon, the carbon-12 isotope and the carbon-13 isotope. Carbon-12 isotope has a mass of 12 and occurs roughly about 99% of the time. Carbon-13 isotope here has a mass of about 13 and occurs about 1% or so of the time. The first thing when you look at a situation like this is you do want to quickly look at the percentages and again, make sure that it does add up to approximately 100. It may not be 100 perfect, but it should be definitely in the 100 ballpark. If you look at those and they don't add up to 100, you're missing something there. Or you're missing an isotope along the way. So basically what we want to do is take each of these and do our math here. So if we were to calculate the atomic mass, we would take our first isotope, our carbon-12. It occurs 98.97% of the time. If I move the decimal point 2 places to the left there, that converts my percentage into a decimal. Again, you could divide it by 100 if you like. We're going to times it by the 12 AMU, which is the atomic mass of my first isotope. So again, everything in here basically is from my first isotope, which is the carbon-12. I then again are going to add this to my second isotope, which occurs about 1.1% of the time. So again, if you don't want to turn the decimal or move the decimal, you could just divide by 100%. Again, I'll do that for you. And you can times it by 13.003 AMU. And if we do that here, so we're going to take 0.9897 and times it by 12. We're going to add it to basically 0.0111 times 13.003. We end up with approximately 12.02 AMU. And again, if we look at the periodic table up there for carbon, we will see 12.01, which is fairly close to what we just calculated here. Any questions on that calculation? So again, in this particular case, we just had 2 isotopes. You could have 3 or more. And again, you just kind of keep that pattern going, percentage times atomic mass of each isotope added to the percentage times the atomic mass of each isotope that's there. Yeah. Which on the screen? Yeah, that's what you would find if you look on the periodic table underneath carbon. And that would be the atomic mass underneath carbon, which is pretty close to what we just calculated there. So that's basically how they sort of calculate the number that you see up there on the periodic table. So again, all the numbers that you see below the symbols on the periodic table are the atomic masses and calculated by taking the average values of all the naturally occurring isotopes and the percentages at which they basically occur. All right, so why don't you try one here? We got bromine, 2 stable isotopes, 79 and 81, and they have a masses of 78.92 and 80.92. Determine the average atomic mass. Take a couple minutes here, should you come up with. All right, so let's take a look. So we have 2 isotopes of bromine here. Again, we are given some percentages, so it never hurts and probably a good idea just to quickly peek at both percentages And when we do, and we add them together, we do get about 100%, which is good. That means we're not missing anything, obviously. So we do have the masses of both of the isotopes there. So we could just go right into our formula here, and our atomic mass will be our first isotope. And again, I'm just going to move the decimal point. Our divided by 100 gives me 0.5070. We're going to times it by the first atomic mass, which is 78.92. We are going to add it to our second isotope, which has a percentage of 49.32%. That converts to 0.4932 when you multiply it by 100 or divide it by 100. We will multiply it by the atomic mass of the second isotope, which would be 80.92 AMU. And if we do all that good stuff, I believe we end up with 79.92 AMU, which looks like it would be D in this case. Any questions on that there? That is, again, if you look at bromine on the periodic table, pretty close to what we see up there, 79.90. Again, the difference is obviously the rounding the percentages and stuff like that, but pretty close to how we get that number. Any questions on that? Now, it's important to remember that technically speaking, we don't really a lot of times call these average atomic masses. We just really do call it the atomic mass of these guys. But for example, like the carbon one that we just talked about in that last example, where there's the carbon 12 or the carbon 13, you would never really find a carbon atom that has a mass of 12.01. You would either find a carbon atom, if you could like pluck them out and look at them, you would find one that is basically the carbon 12 isotope that has a mass of 12, or you would find one that's really the carbon 13 isotope that has a mass of 13 and change. You'll really never find one that has sort of that average atomic mass. Just like here with the bromine, you know, you would find one that has like the mass of 78 or the mass of 80, not really necessarily one that you would have obviously a mass of 79.90. It's just sort of an average value that we use for bromine. Any questions on atomic mass or how to calculate it? Variations of this problem would be they actually do just give you the atomic mass, and maybe they want you to find the atomic mass of an individual isotope, or maybe percentage of an individual isotopes, or a variation of this type of problem. All right, then let's talk about the periodic table. It is the thing hanging on the wall there and here as well. So let's talk about some of the parts of the periodic table. First off, when you go up and down in a group on the periodic table, or up and down in a column, that is a group. And there's numbering on this one, as you can see up here, and also on this big one up here. You'll see some different types of numbering. And sometimes you'll see A numbering like it is up there, and some B numbering in the middle. Most every time you sort of use in a chemistry class the periodic table, we typically use the A numbering or the representative numbering. And that means that group 1 starts with lithium. Group 2 is beryllium. We actually skip all the middle part here. And then right here, boron and down is group 3, group 4, 5, 6, 7, and 8. So we use that sort of representative numbering when we talk about groups. It really is the A numbering, although most people don't say like group 1A, they just say group 1 and so forth. So on this periodic table here, again, this is group 1, that's group 2, group 3, group 4, group 5, group 6, group 7, and group 8. We'll talk about it in just a second, but even though hydrogen is sitting there on top of group 1, it actually is not part of group 1, even though it's kind of sitting there. Group 1 actually starts with lithium, which is below it. Yes, ma'am. They don't count in terms of group numbers, how we number groups on the periodic table. They are a special set of elements that we'll talk about in just a second, but we don't usually use group numbers to refer to those. And some periodic tables like we see here and up there as well will just go from 1 to 18. But very often and most times during chemistry, 1 through 8 is what we use. 1, 2, skip the middle, 3, 4, 5, 6, 7, and 8. Going from left to right, those are periods, and there's 7 periods on the periodic table heading in this direction. And as we also talked about, obviously the number above each of these symbols are the atomic number, which, as we know, is the number of protons that we find in the atom. So groups go up and down, periods go left to right, and obviously the atomic number up on top. And as we also just talked about on the bottom there, below the symbol, the atomic mass that we just talked about how to calculate. When we look at the periodic table, it's basically divided into 3 different sort of categories: metals, nonmetals, and metalloids. On pretty much every periodic table, including the one up there, there's kind of like a red line. There's usually this sort of staircase that is highlighted. And pretty much to the left of the staircase, those guys are metals. Also on the bottom 2 rows, which are not on this picture, but would be down here, those 2 bottom rows are also metals as well. To the upper right of the staircase are nonmetals. And right on the staircase, and some books will include boron as well, but these are what are known as metalloids or semi-metals. Let's talk a little bit about some of the properties of these guys. Metals are good conductors of heat and electricity. They could be hammered into sheaths, pulled into wires. They typically have a very shiny appearance. For the most part, metals are going to be solid at room temperature. The one exception is mercury. Mercury is a liquid at room temperature, which is why, for example, on that periodic table over there, it is a different color. On most periodic tables, at least big periodic tables, it's a different color. It's actually the only sort of metal that is a liquid. Now, a second ago, I just mentioned that group 1 actually starts with lithium and not hydrogen. And that is because if we look over here, this guy right here is hydrogen. This guy is lithium. What is the difference between hydrogen and lithium? Hydrogen is it's a non-metal, right? And lithium is a metal. So everybody below lithium is a metal, which is why group 1 really starts with lithium. Hydrogen is over here because of some special characteristics and properties that hydrogen has. If you're old enough like me and remember, old periodic tables on the walls would sometimes have hydrogen actually in both locations, because it technically is a non-metal that should be over there on the right. But a lot of times it behaves sometimes like a metal, so they kind of throw it over there on the left. But technically speaking, hydrogen is a non-metal. And again, not part of group 1 because of that. All the rest of them are metals there in group 1. Now, nonmetals pretty much have the opposite characteristics than metals. They're bad conductors of heat and electricity. They're dull, they're brittle, they're insulators. A lot of nonmetals will have a variety of states. So some are gases like nitrogen, oxygen, chlorine. Some are a liquid like bromine that has a little bit of a vapor or gas above it. And some are solid like carbon and sulfur. So with nonmetals, you got sort of like every state you can want. There are certain elements, as was maybe mentioned, that actually do come as diatomic molecules, which I think we might have talked about in the earlier chapter. So a lot of our nonmetals are like hydrogen, our nitrogen, our oxygen, our fluorine, chlorine, bromine, and iodine. Remember, these guys are all elements, but they're all diatomic molecules, and how they naturally come are as 2. So a lot of them are gases like hydrogen, nitrogen, oxygen, fluorine, and chlorine. Those are all gases, and they're all non-metals as well. Now, metalloids are also sometimes referred to as semi-metals, and just for an overlay here, you can kind of see it coming down here, and this sort of staircase that comes down. And you can kind of visualize from its location of it's kind of, I got metals to the left, I got non-metals kind of upward to the right. So metalloids are sort of elements that really do sort of fall on both sides. The same element can have some properties that are very similar to what we see in metals, while that same element will have some properties that are very similar to what we see in nonmetals. So kind of makes sense where they're located as you kind of move from metals to nonmetals. You got guys kind of on that staircase that could fall on either side. A lot of semiconductors and stuff like that obviously come from that region of the periodic table. Now, there are certain special names for groups here on the periodic table. We'll start with group 1. Group 1 are the alkali metals. And again, as I mentioned a number of times, starting here with lithium and down, group 1. Right next door to it, beryllium, magnesium, calcium, and all those good guys, those are the alkaline earth metals. By the way, if you don't know, alkaline means basic. And a lot of strong bases actually come from guys in group 1 and group 2. Add it with water, you get things like sodium hydroxide, which is a strong base, potassium hydroxide, calcium hydroxide, strontium hydroxide. So a lot of really sort of strong bases actually come from group 1 and group 2 on the periodic table, hence why they're called alkaline, and alkali metals really means basic. Heading all the way over to group 7 over here where fluorine is, and coming down, these are the halogens. And the last member here of the that's kind of important, which I think will be on the next slide, is group number 8, our helium, neon, argon, all those guys. Those are the noble gases. So in addition to obviously knowing the different groups, you do need to know these names and where they are located on the periodic table. Again, alkali metals group 1, alkaline earth metals group 2, the halogens group 7, and the noble gases there in group 8. Any questions on that there? Now, the noble gases are called that because they are chemically inert, which means they're very unreactive. They're sometimes called noble because it's like set apart. They play with themselves per se. They will not react with others. So there are some noble metals as well, like gold and silver and platinum. You know, those are some very unreactive metals as well. The 2 rows at the bottom are set aside so that they do not make your periodic table ginormous. And we can see that if we follow the atomic numbers. So if we get down to here, that is 57, that is 72. We're missing some numbers there. The missing numbers is actually right here. This row technically should go in there. And right below it, 89 to 104, the missing number is right here. So these 2 rows right here technically should go right there in the periodic table. I've only seen it done once ever, and it had to be done on a wall because it moved everybody else way over out of the way. So those 2 guys technically go in that spot. In the middle was a question earlier between group number 2 and group number 3. That is where we find our transition metals. And our transition metals is sort of how we label that area that's between group 2 and group 3. Transition metals, as we will talk about when we talk about naming, they could have pretty much a variable type charge. So depending on the situation, for example, something like copper could be +1 or +2. So they can have multiple types of charges, which is one characteristic of them. Also, these 2 rows on the bottom, they are called the lanthanides and actinide series because that is technically where they follow those 2 elements. They are also sometimes referred to as inner transition metals, because technically speaking, they should go right there in the middle of the transition metal region. We don't deal too much with those in here, except with nuclear chemistry. A lot of radioactive elements, again, are down in that region on the bottom too. A lot of those guys with the weird names like Einsteinium, you know, Californium, Berkeleum, all those guys, you know, are sort of in that area. Any questions on that there? So for the periodic table, you need to know, again, the groups, which way they go. We need to know which way periods go. You need to know the names of the special group names. You need to know where you find metals, nonmetals, and metalloids on the periodic table. And you need to know some characteristics, obviously, of metals and nonmetals and those kind of guys. Any questions on that? Periodic table that will be provided for you on exams and stuff will have basically the element symbol, no name, the atomic mass, and the atomic number on it. There will be no labels like these are the noble gases or anything like that. They will have probably group numbers on them, but no labels like that. All right, then let us talk a little bit about modern atomic theory and the periodic table. But really what we're going to be sort of focusing in on here is really electrons for the rest of the chapter here for the most part. And we talked about electrons that obviously are negatively one charged. Electrons are found in different spots in an atom. They are in that sort of empty space, that electron cloud, as we talked about. They are traveling in those really sort of random patterns. And when we talk about electrons, as I might have mentioned earlier, there's this idea known as the Heisenberg uncertainty principle, which basically says that the more you know about how like a particle like an electron is traveling, the less you know about its actual position, and vice versa. The more you know about its position, the less you know about sort of how it's moving. So when we talk about electrons in an atom and sort of how they're moving and where they're at, the best that we could kind of think about and come up with is the idea of a probability of finding an electron in a specific location. And we know that, you know, there's a pretty high probability that because the nucleus is positively charged, that there's a good probability near the nucleus, you know, we should be able to find an electron. Just because there's a high probability of finding an electron near the nucleus, it doesn't mean we actually know where it's at, how it's moving, or anything about it, other than there's a good chance at some point there's going to be an electron in that particular area. Clearly, as we move away from the nucleus, there's sort of a lower and lower probability of finding electrons in that area. When we do have electrons, they do end up being on different energy levels. And what oftentimes happens with electrons on different energy levels, so let's just say that the lower energy level here, this is a lower energy level, and these are obviously higher energy levels. Higher energy levels are typically further away from the nucleus. Lower ones are obviously closer to the nucleus. When an atom gets excited, what ends up happening is it picks up a lot of energy. And when these electrons, for example, pick up energy, they decide they want to go to like a higher energy level and kind of go all the way up, if you will. Now, much like most things in chemistry, things want to be at sort of a lower state of energy. That's sort of a more stable situation. So what's going to eventually happen is an electron that gets excited will eventually work its way back down to a lower state of energy, maybe to this energy level here. There's an idea of a conservation of energy, which means energy is never lost, never created, never destroyed. So in order for that electron to come back down in terms of energy, the atom would have to give off that energy in the form of a wave. And it will give off this energy in the form of a wave, which is sometimes referred to as a photon of light. And this happens a lot as electrons are transitioning from one energy level to the next. If the electron started at a lower energy level and went to a higher energy level, does it have to gain or lose energy to do that? If an electron started lower energy and ended up higher, it needs to gain energy to do that, right? As it comes back down from a higher energy level to a lower energy level, it has to give off that energy and lose that energy. And if that energy that is given off as the electrons are transitioning down to a lower energy level falls, for example, in what we like to call the visible part of the spectrum, where we see colors like Roy G. Biv, right? Red, orange, yellow, green, blue, indigo, violet. We will actually see colors. That's sort of the basis of like 4th of July and fireworks. Yeah, they shoot off fireworks. They have different elements in it. They have explosions in it, obviously. The explosions supply a lot of energy to those electrons, Electrons get excited, then they come back down. As they come back down, they have characteristic colors that are given off in that process. And we see all the pretty colors go, ooh, ah. I'm glad I waited like 12 hours to see my 4 minutes of fireworks at night, you know, but that's basically what is happening. You might have done it if you've ever boiled water to make pasta or something on the stove, and maybe it overboils and the water hits the flame. If you have obviously a flame on your stove there or your cooktop, and maybe the flame goes to like a orangey yellow color really quick, and then it kind of goes away. And that's really because a lot of time water will have like salt in it, like sodium. Maybe even put more salt if you're making pasta. And it's the electrons of sodium that basically get excited when it hits the flame. It picks up all that energy and it makes the characteristic color of sodium, which is kind of a yellowish type color and stuff like that. So what we're going to be looking at for the rest of the chapter really is sort of where we sort of house all these electrons in the atom and the different energy levels. But to talk about the electromagnetic spectrum, which is where we see energy being given off, as those electrons transition, if the wavelength corresponds to in this visible part of the spectrum, as I mentioned before, that's really where we see colors. It doesn't always have to give off energy in the visible part of the spectrum. It could be some other part of the spectrum, like the infrared part, where you might feel heat. It's really why we feel heat when we have something like a flame going. We can kind of see the color, and also it's giving off energy in that kind of infrared region, so it feels warm and all that to us. There is a relationship to the wave that is given off and energy. So a wave such as this, which has a really longer, what is known as lambda, that's the wavelength. So if you typically have a wave of energy that's given off with a long wavelength, it usually will have a longer frequency, which is how often it occurs. And that usually correlates to a much lower energy. And vice versa, if you had a wave which looks something like this, as a much smaller wavelength, it occurs much more frequent and has a much higher energy. So smaller wavelength, higher frequency, and that corresponds to higher energy. So if we look at this electromagnetic spectrum on the right-hand side over here, this is a much longer wavelength than on this side, which is 10 to the minus 12, which is a much shorter wavelength. So on the right-hand side are things that are a little bit lower in energy, not as high energy. We see things like radio waves, which is why we are not so bad off from listening to our radio as we drive into the school. Coming up a little bit more in terms of energy, we hit microwaves. Microwaves have enough energy to get water molecules spinning really fast in your food. And then you get like your pizza in 3 minutes, which ain't too bad. Infrared, as I mentioned before, you know, we kind of feel heat coming off in that. There's a little bit more energy. The visible part of the spectrum where we see colors is next. And even within colors, there's a difference in terms of energy. This wavelength over here in the red region is longer than the wavelength like in the purple or violet region. That means that this guy is actually lower in energy, a red color, versus this guy, which is higher in energy on, I guess I shouldn't use blue on blue, higher in energy on more of the violet side. How that relates to, for example, electrons transitioning. If an electron went from like the 5th energy level all the way down to the 1st energy level, it takes a lot of energy to do that. And if it did give off energy in the visible part of the spectrum, we would expect it probably to be towards the purple side. If the electron went from like the 3rd energy level to the 2nd, just a small little drop in energy, right, it's going to give off maybe a color that is going to have a longer wavelength, not as much energy. And maybe we would see a color like red or orange in that area. So as these electrons transition from different energy levels, depending on how far they travel, correlates to how much energy is either released from the atom, and also would correlate to sort of the color that you would see. Ultraviolet is next. That is also very high in energy. That is why we put sunblock on when we go outside, right? So we don't get too crispy, right? And all that kind of stuff. Next is X-rays, which is why they throw the lead vest on you and they leave the room when they shoot the X-ray, right? Because they do not want to be standing there. And all the way at the end are gamma rays. That is like pure energy, basically, radioactive rays. You need a lot of protection. If you ever work with anything that's radioactive that emits gamma rays, you need like some lead and some nice safety things to actually work with it, because it's a lot of energy that gives off. So this is electromagnetic spectrum. You are responsible to know kind of the order, not the exact numbers where anything breaks off. But like if I asked you which one is higher in energy, put them in order based on high energy to low energy, or put them on order from lowest wavelength, longest wavelength to shortest wavelength, or something in that region. That also includes the colors. So, you know, which color is kind of higher in energy, which one's lower in energy. Any questions on what you need to know there? Okay. So I think we are going to lay it up because we need more than like 4 minutes to get into the next topic. So we will lay it up there for today.